Hello everyone. This presentation is going to cover sections 1.2 and 1.3 from the Openstax Chemistry Atoms First Second Edition textbook. In these sections we are going to investigate the phases and classification of different types of matter, as well as some of the physical and chemical properties and changes that they exhibit and undergo. By the end of this presentation, you should be familiar with the three common phases of matter and the fourth uncommon phase of matter, some of their properties. You should be able to classify a sample of matter as an element or a compound or a mixture, and you should be able to determine whether given properties and changes in matter are chemical or physical in nature. So let's get started. Okay, starting from the real fundamental level here. You probably know a lot of what's on this slide, but we're going to cover it real quick. Again, matter is everything and anything that has mass and takes up space. All tangible, real objects and substances we consider matter. Matter commonly comes in three phases. You have your solids, and you have your liquids, and you have your gases. Uh, Solids and liquids have volumes that are independent of pressure, meaning that if you squeeze these things together, you can't really make them any smaller. You actually, they say most of your liquids, water for instance, is incompressible. If you try to press it together, you can't make a sample of water any smaller than it already is. You might be able to come up with kind of a thought of a solid that you can squeeze and make solid, but usually solids that you can squeeze and make solid have some air pockets or something in them that allow them to take up space. If you think about something like a solid metal gold bar, for instance, if you were to squeeze it together, you could not make that metal bar any smaller than it already is. Liquids and gases, however, conform to the shapes of their containers. So liquids, while you can't compress them, they will spread out and they will change shape depending on what container they're put in. Solids are just the shape that they're in until they're affected by some other force. Gases kind of have both things going for them. Gases are compressible, just like that picture we just saw in a few seconds ago. The different gas tanks that we use to transport and store gas, we usually compress it to a small volume and put it in a small container, which makes them easily transportable. They also tend to fill the shape of the container that they're in. The air that you're breathing right now is filling the shape of whatever room you're sitting in. And if it escapes to the outside world, it tries to fill the entire atmosphere, essentially. There is one-fourth less common phase of matter, and it's called plasma. Plasma is generally very high temperature gas, and we're talking very, very extreme high temperatures on the order of 5 to 10,000 degrees. When a gas is heated that much and it intakes that much energy, the atoms and molecules that make up that gas start to split apart. They start to break and come apart into the parts that make up the atom, protons and neutrons and electrons and stuff. And so you get this kind of highly charged, superheated form of matter that we refer to as plasma. You mainly see it out in interstellar explosions, so star explosions and things, big high energy events going on out in outer space. We do see it. There is some generated here on Earth. There's a picture of a supernova. Things that are called plasma TVs, there was an older technology around, a little more prevalent, maybe 10, 15 years ago or so, where plasma TVs were a thing, and the tiny little electrodes that make up the panel in a plasma TV would generate tiny little amounts of plasma that would give you your different colors. Also, especially big lightning strikes create plasma around them. There's that much energy in lightning. So those are the three phases of matter. Again, probably already have some exposure to some of those, but we kind of give some classification to the actual differences between the solid and liquid and gas. And of course, as with everything, not everything always fits into these neat containers. Good example is peanut butter. Is it solid or liquid? But for the most part, we like to try to categorize things the best we can. So we'll see you on the next slide. So of course, naturally, moving on, if we've discussed phases of matter, the next thing we want to discuss is phase changes of matter. So how does matter go from the solid to the liquid to the gas phase? And of course, this is something by this point in your life you've probably observed, at least with the common compound water, right? So we've all seen solid water, we've all seen ice. Liquid water is really, really obvious. And then gaseous water, what we call water vapor, is usually definitely in the air around us. You can see it when you boil a pot of water on the stove or something like that. So if I ask the question, how does matter change phases? Thinking to those experiences with water, you can probably come up with an explanation that involves adding heat to a sample of matter will cause it to change phase. And of course, that's mainly how it worked. We have a phase change diagram down here in the bottom left corner, and you can see we have the solid phase here, the liquid phase here, and the gas phase here. And it shows that if we increase in heat energy, we can move from the solid phase to the liquid phase, and we call that process melting. You're probably rather familiar with that one. And the inverse of that, if we move from the liquid phase to the solid phase, we decrease in heat energy. We call that freezing. And that's another one you're probably already pretty familiar with. The third one we're going to look at is if we add heat energy to a liquid, at some point it gains enough energy and becomes a gas. We move from the liquid to the gas phase, and we call that vaporization. Now you might want to call it boiling kind of in your head and have a little bit of a different word for it, but the technical term for that liquid to gas transition is called vaporization. One that you may not remember what it's called is when we move from the gas phase to the liquid phase, we call that condensation. And a good example of that is when we see our a drink glass sweat on a particularly hot day. What's going on there is water vapor in the gaseous state in the air surrounding that drink, and it cools off. That air with that water vapor in it sits against that drink and cools off so much that the water vapor condenses out of the air and becomes a liquid again on the side of your glass. It's not actually the drink permeating through the glass. There are two more up here that you see that you may not be as familiar with, and I want you to know these two terms and what they mean. The first one is sublimation. So it is possible under certain conditions for some compounds and some elements to move from the solid phase directly to the gas phase, to the gas phase without ever becoming a liquid in the process. I've got animation of that going on up here in this picture right here. What you're seeing there is what they call dry ice, which is frozen carbon dioxide. It's carbon dioxide in the solid state. At atmospheric pressure, so regular out in the open, if you heat up frozen carbon dioxide, dry ice, to room temperature, it turns into a gas without ever becoming liquid carbon dioxide. And you can see the vapors coming out of there. What they've actually got here is a few cubes of dry ice in some liquid water to help it heat up faster and make that really cool vapor effect. That's how most smoke machines work for Halloween and concerts and all that kind of stuff. Well, some of them use vaporized propylene glycol, and some of them use dry ice. You can also see another neat animation of it down here in the bottom right corner, right beside me. That is elemental iodine. So the iodine you go to the drugstore and buy for cuts and wounds and whatnot is actually iodine, a slight amount of iodine mixed in an alcoholic solution, so like a rubbing alcohol solution. Elemental iodine is this really deep purple crystally looking stuff. And again, iodine, when exposed to atmospheric pressure and regular room temperature, it sublimates. It undergoes sublimation straight from a solid to a gas. And you can see these solid crystals forming that vapor down there. That process, again, is called sublimation. Moving from a solid to a gas phase of matter without ever going through the liquid state. And then finally we have the reverse of that, which is called deposition. So sometimes you can have things that are in the gaseous phase move directly to the solid phase. That one's a much harder process to get a picture of or show you an example of, because for the most part, because it's low energy, it happens very, very, very slowly. But a good example is a lot of the times the reason you have frost on the inside of your freezers, especially if you have like one of the small little fridges that freeze up real bad, is because again, water vapor in the air gets very, very cold inside of that freezer and never even has the chance to pass the liquid phase, and it goes straight to the solid phase and deposits on the sides of your freezer. So the phase change moving from gas to solid is called deposition. Okay, let's get down to business and start talking about one of the main topics in chemistry. What makes up the matter that we are investigating? The answer to that is, of course, atoms. In your standard chemistry classes, you always hear atoms make up everything. Sometimes that's not my favorite answer because it implies that we don't know of anything smaller than an atom. Of course, that's not the case. You can see in the kind of crude model of the atom here rotating around that we know of the 3 different building blocks of the atom, if you will. We know about protons, neutrons, and electrons. And so technically protons, neutrons, and electrons make up all pieces of matter. But we like to investigate and discuss the atom, what these small particles arrange themselves into, because that is the most identifiable tiny subunit of matter. And the reason is because these protons, neutrons, and electrons tend to arrange themselves in very identifiable ways. And we tell one atom apart from an atom of a different element by how many protons it has in its nucleus. And you'll see this quite a bit throughout this course. Obviously, this is the periodic table of the elements. And one thing that the periodic table does is it tells you an atom of that element has how many protons in its nucleus. And you can see this number right here, on this particular periodic table, what we call the atomic number, is how many protons an atom of that element's nucleus will contain. So hydrogen, every hydrogen atom has 1 proton. Any atom out there in the universe that you find and pick up, if it's only got 1 proton, we consider that a hydrogen atom. Carbon, any atom that you go out there and investigate and find in the universe, if it has 6 protons, then it is a carbon atom. 8 is how many protons is required to be an oxygen atom. And then gold is a much, much bigger atom. Gold has 79 protons as part of his structure. So this is part of what the periodic table does for us. It organizes that information, and it lets us know how many, we can look at how many protons are in a specific atom and determine what element that atom is. There are currently 118 different identified elements, so we've been able to isolate and study and identify atoms that have anywhere from 1 to 118 protons. As they get bigger and bigger, they get more unstable and tend to fall apart. So we might not, it becomes a science puzzle trying to piece together bigger atoms, because the bigger ones, above about 100, they don't even occur in nature. They've only been made in laboratories. So, but people are still trying to make new ones on a pretty constant basis, and probably will succeed. But as of right now, there are 118 different ones that we have isolated and identified. So oftentimes atoms arrange themselves into what we call molecules. Molecules are formed when atoms join together via chemical bonds. So the atoms, when they're bonded together, they will move around as a unit until those bonds have been broken, usually via some chemical reaction. Molecules can be composed of 2 or more atoms that are the same element, or molecules can be composed of 2 or more different atoms, at which point we then call them compounds. You can see some models below. Over here on the left side, we have some elemental molecules. So these are molecules only made of atoms of one type. You see an oxygen molecule floating around there. You see a nitrogen molecule floating around there. Again, those two are models of the molecules that you are currently breathing in and out. Those two molecules make up approximately 99% of the air in Earth's atmosphere. The other two molecules you see floating around in there are helium and hydrogen, also two gases. And so all of those things would be considered an element. If you had a container full of each, they would be considered you just had elemental oxygen in a container or elemental nitrogen in a container. On the right side, you see some molecules of some compounds. We have the H2O molecule that kind of floating around in there. That's the green and orange. And that is obviously representative of water, H2O. And so every water molecule will have that structure. It will always have two hydrogens chemically bonded to an oxygen, and they will always exist together and always move around together until something is done to break those chemical bonds, usually via, again, some chemical reaction. The other two molecules that you see there, the blue and the green, is representative of an ammonia molecule, NH3. So that's a nitrogen blue atom on top and 3 hydrogen atoms bonded to it. And every ammonia molecule will be the same because that's the formula. That's how ammonia is put together. If you have a mixture of ammonia, if you have some glass cleaner somewhere at your house, then you have a mixture of ammonia. You have those molecules floating around inside some water molecules or mixed with some water molecules. And then finally, the other one floating around there with the double bonds that you see, the oxygen's double bonded to the carbon, that is a carbon dioxide molecule, CO2, 1 carbon and 2 oxygens. And the carbon dioxide will always have that formula, will always have the 1 carbon and the 2 oxygens, it will always have that structure, and those atoms will exist together bonded like that until acted upon by some kind of reaction. Those are all examples of compounds because they always have those fixed ratios. Water is always H2O, ammonia is always NH3, and carbon dioxide is all CO2. This is just a fun TED Talk video. If you have the time, take a minute and watch it. It's not very long, I don't think. But all it is talks about the relative size of the atom. So it's one of those videos that talks about if we blew up an atom to the size of a soccer ball, then it would fill up, a glass of water would fill up 20,000 Olympic-sized swimming pools or something. But it really kind of gives you an idea of just how small atoms and other atomic particles are. There's not anything in the video that you're responsible for, so you're not forced to, but it's a fun video and a short watch. Give it a try. So we're going to learn to classify matter in the next few slides, and the two of the classifications that you're going to make are whether something is a pure substance or whether something is a mixture of substance. What chemists consider to be a pure substance is either an element or a compound. Elements, we've already determined, cannot be broken down into any simpler substances by chemical changes. That is because every atom of an element is the same, and we can't break down atoms by chemical reactions. We have to get into nuclear processes to break down atoms, and that's where we start to get into the physics side of things. So elements can't be broken down. They are only one type of atom. You can't separate out those atoms and get anything different. An example of an element here on this page is the diamond that you see. Diamonds are composed of only carbon atoms, and so therefore it's a pure substance. It's no mixture of anything. It's all carbon atoms all bonded together in a very, very nice crystal. If you try to subject diamond to a chemical reaction, you could break those bonds and break it down into a finer powder, but you would still only have carbon when you were done with it. You can't change it or make that diamond into anything other than carbon without adding other matter to it, so it's considered an element. Also, compounds that we just discussed are pure substances as well. Compounds are things like water, which has a fixed composition. So a water molecule will always have the formula H2O. You will always have 2 hydrogen atoms and 1 oxygen atom all bonded together like we just saw on the last slide. And if you have a sample that is nothing but those types of molecules, then you would say you have pure water, and we still consider that a pure substance because it is the same all the way through. Every piece of that is the same. These two are the only examples. Compounds and elements are the only thing that we call pure substances. Everything else not considered a pure substance is formed by mixing pure substances together. We have 2 different mixtures that we are going to try to be able to differentiate between, and those are heterogeneous mixtures and homogeneous mixtures. Heterogeneous mixtures are mixtures that you can see the different parts of generally. They have variable composition in different parts, and oftentimes it's possible for components to settle out of a heterogeneous mixture. You see some examples there in the pictures to the right. We love to do food examples for the heterogeneous mixtures. They're just very easy to identify. The oil and vinegar salad dressing that you see there, obviously if you let that sit, then you will come back and find that the oil and vinegar layers have separated. You have to shake it up again to get it mixed back up. You can see the different spices in there. You can see the oil and the vinegar not mixing, and so that's what makes that a heterogeneous mixture. I like the next example because it shows that mixtures don't necessarily have to be liquid. That's what some people often think of when they think of mixtures. But granite is a mixture of different minerals, and it doesn't have a uniform composition. Some parts have more of one mineral than another. It's not really possible. Granite's not really going to settle out, but you can still see the different parts that make it up. And then finally, there's another food example, Chex Mix. Right? It can have variable composition. One handful of Chex Mix might have a lot of pretzels, which is no good. But another handful of Chex Mix might have a lot of the little crunchy bread things that are really good. So heterogeneous mixtures might be different as you sift through them. On the reverse of that, we have homogeneous mixtures, which are uniform throughout, and generally they don't settle out of solution. A good example of that is our friend Red Gatorade there. He's a nice mixture of water, sugar, and red number 40 or red number 4 probably, with a few electrolytes and other flavors and stuff added in, but the main components of that guy are water, sugar, and red. And so the thing is, you can't tell those things apart. One swallow of that Gatorade is going to have the exact same amount of sugar as another swallow of that Gatorade. Also, they are uniform throughout. You can't see the sugar. You can see the red, but you can't tell one a lot of red from another little bit of red. And so that solution is considered homogeneous. Also, a good example of a solid homogeneous mixture is the brass in the instruments that you see there. Brass is a mixture of tin, zinc, and copper, and you won't be able to tell those metals apart. If you let it sit for thousands of years, they're not going to separate from each other. So brass is an example of a solid homogeneous mixture. And then our final homogeneous mixture that we see there is air. We can't tell the different parts of air apart. One sample of air generally has just as much nitrogen and oxygen as another sample of air. So it's considered a homogeneous mixture. You will be asked to differentiate between heterogeneous and homogeneous mixtures on some of your assignments, so you can kind of get an idea of the difference between the two. And so here's a handy little chart that can show you the overall breakdown of these categorizations of matter. We can see that, first of all, our first categorization is whether matter is going to be considered a pure substance or whether it's going to be considered a mixture. And then further down past whether you've determined you got a pure substance or a mixture, do you have an element, or do you have a compound, or do you have a homogeneous mixture, or do you have a heterogeneous mixture? The elements will be things that are all composed of the same type of atom. The example that the chart there gives you is a copper teapot. It would be nothing but repeating copper atoms making up that elemental copper teapot. The example that I have floating around here would be elemental oxygen. So inside of a therapeutic oxygen tank is pure elemental oxygen, and that would look like a bunch of these O2 molecules. So, but notice they're all the same atom. They're all that oxygen atom with 8 protons. They're floating around and flying around and bumping around inside of that tank, but it's considered an element because there's nothing but oxygen atoms contained within that tank. Pure substances, again, can also be compounds, and in a compound the molecules are all the same. That's the important thing, is that the molecules are all the same in a compound. And so the example they give down there is baking soda, which has the formula NaHCO3, meaning baking soda has some sodium, some hydrogen, some carbon, and 3 oxygens. And every baking soda molecule will have that same structure. Just like water here, water is a compound also, because if I took a sample of water, if I had a glass of water, every molecule in that glass is the H2O structure that you see there floating and swishing around inside of that glass. Now, if I went to mix some things with that water, if I added some sugar or some salt to that water, at that point I would have a mixture, because everything contained in the glass is not necessarily NH2O. It also has some sugar molecules in there floating around and dissolved in it. That would probably be a homogeneous mixture, right? Salt and sugar dissolve well into water, and we can't tell the different parts of the mixture, so it would look like all one solution. If we were to add something to it to make it a smoothie or something where we could see different parts, maybe some different fruit pulp flying around or something like that in there, At that point, we would have a heterogeneous mixture. So we're going to be looking to categorize some of the properties of matter as well. We have two broad classifications of properties of matter, that is physical properties of matter and chemical properties of matter. Physical properties of matter are things that can be measured without changing the substance into something else. They're generally rather common properties that you probably have had exposure to. They are things like if you talk about the color of an object, you describe one of its physical properties. If you talk about the density of an object, you've described one of its physical properties. Hardness is a physical property. What phase the matter is in, so whether a matter is solid or whether it's liquid, that's describing a physical property. And then other ones that you see down there are the melting point and the boiling point, and those are, of course, the temperatures at which that happens for that substance. For example, a physical property of water would be that it melts at 32 degrees Fahrenheit or 0 degrees Celsius. A physical property of water would be that it boils at 100 degrees Fahrenheit or 100 degrees Celsius or 200 degrees Fahrenheit, 212 actually. And then another one finally down there is conductivity. So whether something conducts electricity or not. Generally metals conduct electricity and stuff that is non-metallic does not. And heat conductivity as well. Do things conduct heat really well, or are they good insulators? You can measure all of those things. You can figure out all of those things about a substance without chemically changing or without it undergoing a reaction and changing into anything else. That makes them the physical properties. So the other category of properties that we'll see are chemical properties. And chemical properties just generally describe whether or not a substance, a sample of matter, is able to change itself into another sample of matter. Examples of things that can be chemical properties is something flammable, the flammability of a substance. So is gasoline flammable? Of course it is. Can you test whether it's flammable without changing it into something else? No. When you burn something, you convert it into other materials. And so to test for flammability, you have to change that matter into something else. Toxicity to living organisms would be considered a chemical property of matter. The acidity of something, so the pH of that substance, would be considered a chemical property, because when you test it with the testing solution, you actually do change that substance. The next one is oxidizability. So the word oxidize means to have oxygen atoms added to it. That's a fancy way for saying rusting. Will something rust? Is whether or not something is oxidizable. And of course, something has to be changed into rust to determine whether something is rust or not. And then there are some other forms of reactivity, but in general, if a property has to be, if you need to change that substance to determine whether that substance is that property, then you can consider it a chemical property. One more further division of the properties of matter is whether or not a property is intensive or whether it is extensive. Intensive properties do not depend on the size of the sample. So if the property doesn't change with size, then it is an intensive property. Color doesn't change with size. The density of something doesn't change in size. If I have a glass of water in one hand and a bucket of water on the other hand, they may have different weights, but they have the same density. Smell doesn't generally change with size sample. It may become more apparent, but it's the same smell, whether or not you have a small one or a big one. Taste is the same way. Luster is a good example. Luster is how shiny something is. So if you have a small piece of gold versus a large piece of gold, you may want the large piece of gold more, but the shininess of the small piece of gold is just the same as the shininess of the large piece of gold. Same goes for hardness, so we could do that with diamonds. A tiny little diamond will have the same hardness, be just as hard as a large diamond. And then finally, temperature is not an intensive property. If I had a pot of boiling water on the stove and I remove a spoonful of that pot of boiling water, both the spoonful of the water and the pot of boiling water, for a brief moment at least, have the same temperature. They both would be 100 degrees Celsius. Now, on the other hand, extensive properties do depend on the size of the sample of the matter. And those are things that kind of sound like they depend on the size. Things like mass. How much matter is in the object? That depends on the size. Volume. How big is it? Well, that obviously depends on the size. And that follows with weight. How many molecules? But also, interestingly enough, there is heat on there. Heat energy and temperature are not the same. Let's go back to our example of the boiling water on the stove. If I pulled out a spoonful of 100-degree water and I poured it on myself, it would probably hurt. But I probably would be okay. If I were to take that pot of boiling water and dump it on myself, I would be in a lot worse situation. And the reason is because even though they're the same temperature, the heat energy contained within the spoonful of the water is much, much, much less than in the entire pot of boiling water. So heat energy is an extensive property, while temperature is an intensive property. We can also divide changes that we see in matter into physical changes and chemical changes. Physical changes do not change the chemical composition of the substance. So just like a physical property doesn't need to be changed to measure it, a physical change doesn't necessarily change it into any other compound. There are some examples of physical changes that you see down here. All of your phase changes are physical changes, because when we change, for example, ice into liquid water into steam, all of those things are still water. The H2O molecules did not change. They may be arranged differently. They may be moving a little bit differently, but they are still water molecules. Also, things like cutting, smashing, and grinding. You see the animation of the tire going through the industrial shredding machine out there. It's kind of neat. The rubber bits that come out of the other side are still the same compounds that made up that tire before it was shredded in the shredding machine. So that's a physical process. We didn't make any new compounds. We don't have a new material coming out of the other side, even though it's not in the shape of a tire anymore. So those are physical changes. And then finally, to wrap up section 1.3, we have the chemical changes in matter. And you can probably gather up to this point, a chemical change is something where a sample of matter is changed into a different substance entirely. A chemical reaction happens and a material is changed from one thing into another. And we've got some examples down here. Wood burns to ash and carbon dioxide. You digest the banana you had for lunch. Steel on a bicycle left in the weather starts to rust. It starts to change from nice steel to iron oxide, which is rust. And if you pour baking soda and vinegar together, you get some salt and you get some carbon dioxide, and that's where you get all the nice bubbling from. So chemical changes happen when a sample of matter is changed into an entirely different substance. This doesn't always bear to be the case, but a lot of times you can tell the difference between a physical and a chemical change if the process is reversible. If you can take what you ended up with and make what you started with, again, it's usually a physical change. If the thing that you started with is completely different and you can't reverse the process, good chances are that that was a chemical change. This is the end of section 1.2 and 1.3.